Hi guys, I'm Jackie. I'm a first grad student here at Curtin. We here have been having some problems with organic chemistry in regards to structural isomers of alkenes and branch chains. So we're going to be here talking to Mauro Mocerino, who's an expert of that kind of stuff, and hopefully that'll sort some problems out for you.
Hello, welcome to Curtin University. My name is Mauro Mocerino and I'm a lecturer here at the university in the Department of Chemistry. Today I would like to talk to you about organic chemistry and give you a few pointers on how organic chemistry works. Organic chemistry is a very large field of chemistry. There are well over 10 million compounds known, and so the variety and complexity is quite large. However, there are fundamental building blocks and rules that you need to know, and once you know that, you can go a long way. I'd like to start this tutorial by considering the alkanes. They are the building blocks of organic chemistry, and for your studies you will need to know the first 8 alkanes. The simplest of the alkanes is methane with 1 carbon. A model of methane here is shown where the black bit represents the carbon and these things are the hydrogen atoms. Methane is the simplest. The next one down is ethane with 2 carbons, propane with 3, butane with 4, and then pentane, hexane, heptane and octane as the last 4. Now from experience it seems that most students seem to have troubles remembering the order. A simple way of remembering it might be, for the first 4, monkeys eat peeled bananas, M standing for methane, eat ethane, peeled is for propane, and bananas for butane. This is the bit that causes most students problems. The next bit, most students are comfortable with their geometry and recognize pentagons, hectagons, heptagons and octagons, and they correspond to the 4 other alkanes. Okay, now I would like to consider the functional groups in organic chemistry. The functional groups are the reactive portions of organic molecules. Now, the alkanes can be thought of as the framework that holds the functional groups together. There are a series of important functional groups that you will study in your Year 12 chemistry. One of them is alcohols. And the alcohols have the general formula, a carbon bonded to an oxygen bonded to a hydrogen. And given that carbon has 4 bonds, there are 3 other groups attached there. They can be hydrogens or they can be other carbon groups. So they are alcohols. The alcohols are classified as primary alcohols, and a primary alcohol has 2 hydrogens and a carbon attached. A secondary alcohol will have 2 carbons and 1 hydrogen, and a tertiary alcohol we have 3 carbons attached to the carbon with the OH group. Another important functional group we would like to consider are aldehydes. And these compounds have a carbon-oxygen double bond, a hydrogen, and another group here which can either be a carbon or a hydrogen. For a simple example, let's make that a methyl group, so we have ethanal, or commonly known as acetaldehyde. That is an aldehyde. The ketones are very close cousins to aldehydes. We have also a carbonyl group, but here in ketones we do not have a hydrogen. They both must be carbon groups. And a simple example here would be propanone, sometimes known as acetone, and that's a common ingredient in nail polish remover. Now, if we're moving along, a 4th functional group we might consider are carboxylic acids. And in a carboxylic acid, again we have a carbon-oxygen double bond. This time we have an OH group attached to the carbon and some other group here. It can be a hydrogen. Methanoic acid would be that compound. or it can be a carbon, and here we have an example of acetic acid or ethanoic acid. The final two functional groups I want to discuss here today are esters. And esters are derivatives of carboxylic acids where you still have the carbonyl group and the carbon oxygen, but instead of a hydrogen, we have another carbon group. So a simple example would be an ester of ethanol, where ethanol is the alcohol portion, reacts with the carboxylic acid portion of acetic acid or ethanoic acid, and you form ethyl acetate or ethyl ethanoate. This is a common ingredient also in nail polish removers. The final functional group we want to talk about are the amines. Now, you may have heard in your studies of things like amino acids. The amine part is present along with the acid part in the molecules. And the key feature of amines is that it's like ammonia, except that one of the hydrogens of ammonia has been replaced with a carbon. So a simple example would be methylamine or methanamine as an example of an amine. Now, amines are derivatives of ammonia where one of the hydrogens has been replaced with a carbon group. You can have more than one hydrogen replaced, but that's something you'll learn about next year when you do your university studies. Okay, these are the key functional groups. These are the portions of the molecules that give organic compounds their reactivity. The structure of organic compounds is also an important issue. One of the one of the class of compounds that you will be working with are alkenes. Alkenes can be described as a functional group, and they're compounds where we have a carbon-carbon double bond. So if you have a carbon-carbon double bond, you have an alkene. Alkenes are a little different to alkanes because in an alkane, and if I take a model of, say, for example, butane here, in butane, or alkanes, any alkanes, we have rotation around the carbon-carbon bonds. So we have complete rotation around all these bonds, and so it can take lots of shapes. They're not fixed in one shape. With an alkene, if we consider an alkene with 4 carbons, like a butene, they have a double bond in them. And the double bond means that you can't rotate around that bond. So if you consider the double bond, and we have the compounds butene, we can have the methyl groups opposite. And when they're opposite, we refer to that as trans, or the methyl groups can be on the same side. And we'd refer to that as cis. Now here I have a model of cis-butene and a model of trans-butene. The two compounds are different. You cannot convert one to the other. When we were looking at butane, we can rotate that. So that looks a little bit like cis-butene, but because we have a single bond, we have rotation around the bond. An important reason for drawing the alkenes in this sort of way is that it's clearly shown whether you've got, for example, cis-butene and trans-butene. Why do we want to show the difference? They are different compounds. They have different physical properties and different chemical properties. So if you drew your alkene in the unpreferred manner, we can't tell which butene are we talking about. But if you use this manner, you're clearly indicating cis or trans. And so you know which compound you are looking at. Now, there are to round off this tutorial, just as an exercise of the sort of questions you may be asked and how you'd go about solving the question. If you're asked to draw the structure of a compound like 2-methyl-2-pentene, the first thing you would do is look at the end of the name. The end of the name tells you you have an alkene. So we draw our alkene in. You're told that it's a pentene, so we know there's 5 carbons. And we know that the alkene starts at carbon 2. So we can have carbon 1 here, 2, 3, 4, 5. We now have our 5 carbons. Now the name doesn't say anything about a cis and trans, but you're told that on carbon 2 we also have a methyl group. So now we've got CH3, CH3, a hydrogen there, that becomes a CH2, and this stays a 3H3. Because all carbon always has 4 bonds, we just fill in the extra hydrogens you need to make the 4 bonds. So now we've got our pentene, 2-pentene, and it's 2-methyl. We can see here immediately that we don't talk about cis and trans, because if we swap these things around, we'll have the same compound. So drawing it like this, you won't get confused. And when asked to do a problem of this form, always start at the end. Find out what functional group you're working with. Then the next thing you do is find out how many carbons you need to be dealing with, draw them out, and then look at anything else that might be attached to the carbon chain. A second question that's commonly used and helps you understand the functionalities or the bonding within alkanes is a question of the form is draw all isomers of C6H14. So they're isomers of hexane. Now, there are many ways of doing this. One of the ways I would recommend is you start by drawing out, obviously 6 in a row, 1, 2, 3, 4, 5, 6. Then we can have 5. I'm taking a shortcut here and not putting in the hydrogens. You can add them in later. If we have 5 in a row, we can put a carbon there, or a bit sloppy with my drawing, a carbon there. So we can have 1, 2, 3, 4, 5. So this will be 2-methyl pentane, and this is 1, 2, 3-methyl pentane. If we move along further and put a methyl group at this position, that's the same as this one. So 2-methyl pentane, we could count from this end. If I had the methyl there, it'd be 1, 2-methyl pentane. So they're the same. So there are 3 isomers we can do. The next step down, you would look at 4 carbons in a row. Now we've got to put two other carbons on this chain. We can put them both on the same carbon, or we can put them on separate carbons. And now we have all 5 isomers. We can't put a 2-carbon chain on. If, for example, I decided to put a 2-carbon chain on, now my longest chain is a 5-carbon chain. So this structure here that I have drawn is actually the same as this one here, 3-methyl pentane. So these are the 5 possible isomers that we can have. And this is a common question that you may encounter in your studies. It's important to practice drawing structures because organic chemistry seems fairly complicated because the molecules can be large. However, the basic rules of putting together, it's like Legos. If you know how to use Legos, you can do organic chemistry. Just putting the pieces together.
Hi guys, hopefully that helped you out. If you still have any issues with chemistry in general, just go to the links that we've given you or ask your chem teacher, they're probably your best resource. Good luck with exams and hopefully we'll see you here at Curtin.